This video is a kinematics example problem, projectile motion. This is part 2. We are going to be building on information that we got out of part 1, so you may want to watch that video first if you haven't already. So this is part 2 of our kinematics projectile motion example. In part 1, we answered part A of this question, how far from the base of the cliff does it land? And in doing that, we made two important discoveries. First, we found how long it took to land. This is the amount of time that it's in the air, and it's 5.15 seconds. And we also found this delta x, horizontal distance from the bottom of the cliff, was 530 meters. So now we are going to tackle part B, how fast is it going when it lands? Another word for this is impact velocity. So here we're just looking at what we know about the problem again. I have a sketch which shows an initial launch velocity, total initial velocity of 35 meters per second. I've created a table where I've broken it down into its x component. Horizontally, the initial launch velocity is 30.3 meters per second, and the vertical component, so it's also moving upwards at 17.5 meters each second at the launch time. The cannonball travels 40 meters down to the sea, so that's a vertical displacement, and it's negative. And then it travels outwards 530 meters. Clearly my drawing is not to scale here. All of this takes place in 5.15 seconds. The horizontal acceleration is 0. Nothing is pushing or pulling it in the horizontal direction as it moves. This is going to be critical for answering this question about the impact velocity, because this tells us that v final in the x direction is the same as v initial was in the x direction, because nothing pushes or pulls it as it moves along. There's no change, and so we have 30.3 meters per second horizontally at the beginning, 30.3 meters per second horizontally at the end, and it's the same all the way through. I cannot say that about v final in the y direction, the vertical, because there is an acceleration in the vertical direction. So we're going to have to solve for this before we can find the total final velocity, or the total speed right before the impact. We're going to have to combine the horizontal and vertical components in order to find that total final impact velocity. If I take a look at my variables, I'm looking for a v final. I know v initial, I know acceleration, I know time, I also know distance. I actually have a couple of choices as far as which equation to use. I prefer to use this one, that v final in the y direction is equal to v initial in the y direction plus acceleration in the y direction times time. I like this one because I don't have to square anything. I don't have to take square roots. I find it to be a little more straightforward. I feel like I'm less likely to make a mistake. Although really, you could use other equations as well. So if we go ahead and put in numbers, I don't know my final y. That's why I'm doing the problem. I do know that my initial was 17.5 meters per second. That's a positive. And then I'm going to subtract off, because I have a negative acceleration, 9.8 meters per second squared. And we'll multiply that by the time, 5.15 seconds. Nice. This is the nicest looking equation we've worked with this whole time. So to put this through my calculator and solve for it, my final y velocity turns out to be negative 32.97. I'm going to carry some extra sig figs here. So the reason it's negative is that the cannonball is moving downward when it hits the water, so that makes sense. I am not actually finished with the problem. I know the x component of my final velocity is the same as the x component of initial velocity, and now I've solved for the y component of my final velocity, but really I need to still put them together. I have the components, I need to solve for the net or resultant final velocity. So here are my components. My x component is 30.3 meters per second. It's positive. It's moving forward. The way we drew that was to the right. And then my y component is negative 32.97. That's moving downward. So this is a vector addition problem. I'm going to draw these out in our tip to tail method. So the x component moves to the right, 30.3 meters per second, and then I'm going to add to that a downward almost 33 meters per second. So then my resultant goes from the beginning to the end, something like that. So I need to find the length of this vector, that's the magnitude. I also need an angle to describe the way this is moving. So the length, I'm going to use Pythagorean theorem. So my total V final is going to be equal to the square root of my V final in the x direction squared plus V final in the y direction squared. So V final is going to equal the square root of 30.3 squared plus 32.97 squared. These should have units, but again, I have trouble writing on the screen, so I'm going to leave them off so that there's just less confusion. Alright, I'm going to put this in my calculator. So out of my calculator, if I round this off to 2 sig figs, I'm going to get 45 meters per second. So now I need the direction. I can pick really whichever angle I want. I kind of like this angle. I'll give that as an angle below the horizontal. So in that case, I look at the information I have, and I have my V final y, my V final x. I'm going to use an arc tangent to find this. So here's how this looks. Tangent of that angle I picked is going to be equal to the y component divided by the x component. So that would be a negative 32.97 divided by 30.3. So to find the angle, I'm going to take the arctangent or inverse tangent. And that is going to lead to calculating an angle of, it's about 47 degrees. And it comes out negative, and that's because we're measuring the way I've drawn it. If you take a look at it, that's measuring clockwise from the x-axis. But I could say 47 degrees below the horizontal, and that covers it. So we have actually our final answer. V final is 45 meters per second at an angle of 47 degrees below horizontal. And now we've completed both parts of our kinematics example.